welcome back into episode 3 with the amazing Dr. Bill Andrews. So today in the Curing Aging series, we're going to be talking how we age. So Dr. Bill, can you give us a little bit of a recap of the last 2 sessions and then why we're going into now how we age? So we talked about evolution, we talked about the from a historical point of view, why aging came about. And walk us in.
Sorry, we talked about what aging is, and that's really simple explanation. That's just a decline and failure of body parts, to organs and tissues, and it's that's all it is. The next time we talked about why we age, that's why evolution. Why we age, but more importantly, why did we never evolve a way not to age? And it turns out, I'm going to turn my phone off here just a second because I just got another.
No, I'll take these off.
Okay. So we talked. So the question, we talked about why we age, and more importantly, why have we never evolved a way not to age? You would think that evolution would be doing great things for us to overcome this dumb thing called aging. But it turns out that evolution is all about survival of the species, not survival of the individuals within the species. And it turns out that eliminating the longer lived is actually beneficial for the species because it increases the diversity within the species by promoting the offspring interbreeding as opposed to the parents rebreeding.
Yep.
Okay. And so there's a lot more diversity that results, especially when you consider that mutations are always occurring. Mutations result, diversity results, and the more diversity within a species, the more likely it will survive a rapidly changing environment, or at least some members of the species will survive the rapidly changing environment and continue to propagate the species. So, I mean, I want to make a point is that everybody is looking for theories to explain why we age or what aging is and why we age. But there is no need for theories. I mean, I think most of the people don't really have, in fact, I know that most people that talk about evolution and why we age and what aging is and how we age, they actually don't have backgrounds in biology like I do. And, my background is my PhD is in molecular and population genetics. Population genetics is the how and why of evolution, not the what and when that most people talk about. Mm-hmm. Okay, and but I've been studying the things that I need to know to cure aging my entire life, all through high school, college, everything. It's like, what do I need to do what do I need to learn to be able to cure aging? And a lot of it is statistical theory, probability, logic, common sense, all this kind of stuff. Taking actually courses in common sense is something that
It's such a thing.
Yeah, there is such a thing. And but it's like it has allowed me to have the right tools to be able to look and plus, well, in addition to all that, I've done a tremendous amount of biology studies. Okay, and so I understand the mechanisms that occur inside cells, how everything works. And so I can put it all together and come up with an explanation that most people can't come up with. And that's why I say there's no theories needed to explain what aging is, why we age, or how we age. It's obvious. I mean, it's like inevitable, given everything about us and other species too on this planet. It's inevitable that for a species to be successful, evolutionary, it has to evolve an aging process. And that's what I explained last time in our webinar on why we age.
And now we sort of want to get into the meat and potatoes of this course, which is really how we age and why we can overcome that now, or to a degree. That's what you're working on, and that's what you've been working on for a long, long time, and you've gotten us a fair way along on this passage. And then also we'll be able to sort of work out how long is it going to take before we actually will be able to stop aging. And you've got a very good model for that, and working on that flat stick. So let's progress now into the how do we age part of the equation. So we now know why evolution did this and why it knocked us off when we got older and we brought up our offspring, and then we wanted new genetic material brought in and so on. How does the actual process of aging work?
Okay, well, first, let me just comment that the next webinar on how not to age, I think, will be the most exciting one when I get a chance to talk about what the research that I'm doing to eliminate aging and make us all look, feel, and behave 25
so
again.
Don't go anywhere, everybody. You've got to stay around for that punchline, so to speak, okay? But to understand this whole background, so how is it that we age? When we have the hallmarks of aging, are they? What do you think about the hallmarks of aging?
They're all true. Okay, yeah. They're all true, but and I'll come back to those in a second because I was going to mention it. But I want to point out first that aging isn't just a result of random events, like random mutations to DNA or random damage. And we know that from like statistical theory, okay? When we look at a graph of the age people are when they typically die, okay? Well, if aging and dying was totally resulting from random events, it would be a bell curve, okay? And let's imagine first that aging is caused by, or death is caused by one thing, okay? And that is like running across the field with machine gun fire, okay? Well, everybody has a certain probability of making it. Some people aren't going to make it, okay? Well, if you look at the age that people die from running across that age field, it's going to be a perfect bell curve, especially when there's only one thing. Okay, some are going to die their first time, some are going to die, their 1,000th time, and some people, and most of them are going to die somewhere in between.
Yep.
But now, aging, we know that aging isn't caused by just one thing; it's caused by an accumulation of things, and so that only shifts the bell curve to the right a little bit. So the bell curve is now going to require an accumulation of things. It's going to change the shape of the bell curve a little bit, but it's still going to be a bell curve, just shifted over for a while. But we don't see that either when we actually look at studies. What we see is, we see a big death rate at the beginning from newborn babies having high mortality rates. But then it's pretty flat and level with nothing for a long time. And then it starts to increase. Let me get my finger in that. Starts to increase, and then it goes really fast high up and then drops like a cliff.
Yeah.
Okay. I mean, typically there's studies showing that if you are a healthy, very, very healthy, with the best doctors in the world, very healthy 89-year-old, you have an 11% chance of dying before you turn 90.
Wow.
Okay. That's and it gets worse when you get older. Okay?
Yeah.
Well, that drop-off rate is way higher than a drop-off rate for somebody that's younger. So something is happening. There is a mechanism. It's programmed or something. There is something that is causing a limit on our lifespan. Okay, so now that's what all the theories are about. Like, what is that? So, there's a whole bunch of theories. Like in a lot of my talks, I list about 20 of them that have been existed, all the way from the size of an organism affects their aging. There's so many things. I don't want to go into them right now, but I could if you wanted me to. But the point is, there is no need for theories because it's fully explained without any theories. Okay, and aging all starts with wear and tear. Okay, and that's pretty much the hallmarks of aging. Okay, almost all of the hallmarks of aging, except for one, which I'm going to be talking about at the next webinar, is a wear and tear issue. Okay, it's like either it's mutation rates or just a host of different things. I don't have the list of all the hallmarks of aging in front of me, but they all pretty much result in wear and tear.
Yeah. So you know,
What's
oxidative,
that?
oxidative
Yes.
stress and chromosomes, not being
Yes.
read correctly, and proteins misfolding, and telomere shortening, obviously, which is your thing. All of these aspects are all basically a wear and tear sort of a model. So it's a death by 1,000 cuts. We're getting a little bit of a radiation today. We're getting a bit of environmental toxin tomorrow. We're getting, and it's just accumulating.
Well, the only hallmark of aging whose mechanism of action is not wear and tear is telomere shortening. Okay. And I mean, there is a mechanism of wear and tear that causes telomere shortening, but it's not very predominant, and it's very easy to control by just having a healthy lifestyle. So it's the wear and tear from telomere shortening that actually causes a lot of people to die young. Okay, but you don't have to if you just lead a healthy lifestyle and
so smoking and and too much drinking and all the things we already know. Yeah, lack of exercise.
But the very first stage of all of aging is wear and tear. Okay, and there's multiple ways of having wear and tear. But now the question that I used to ask myself even in high school, okay, was, well, so you have these cells in your body and they get destroyed by wear and tear. Well, why doesn't other cells in the body just divide and replace those cells? Okay, just like a bacteria culture. Okay, and theoretically they should, and they do. Okay, and I'll go into a little more detail on that in a minute, but we do have the ability to repair all cell division, not repair. Okay? There's a lot of talk about repairing cell damage, but that's actually not as true as you think it is. But we have the ability to replace damaged cells.
Yeah.
Okay. This should allow us to live forever. Okay, so the best way for me to really get into the meat of it is to start off with the fact that all organs have some cells, all organs and tissues have some cells that are considered the frontline cells, okay, where all the action occurs. Okay, so these cells, they're doing all the work, and resulting from all their action is causing wear and tear in them. So a cell who's actually actively producing or doing all the fighting the battles and doing the work that the organ or tissue needs to do, they have wear and tear. And a typical frontline cell dies on the average of once a year. Okay, none of them last longer than a year on average.
Wow.
And that includes, I mean, when I talk, I typically show an organ as being like a ball with the cells in the front line on the surface of that ball. But not all tissues and organs are like that, and especially the blood. But the blood still has its frontline cells, and they're doing all the action. Okay, so if we have our frontline cells dying on the average once a year, and other cells can divide to replace those cells, we should never age.
No,
okay,
it's a perfect circle. Yeah.
Let me, in terms of mutations, let's say the easiest example of why wear and tear to a cell would be mutations. And there's three kinds of mutations. There's mutations that are harmful to the cell. There are mutations that are beneficial to the cell, and there are mutations that are neutral to the cell. Okay, so if the mutation is harmful to the cell, that cell is going to die quickly. Okay, because it's harmed. It's not going to be able to perform its function. It's going to die faster, and so instead of a year, it's going to last like maybe 3 months. Okay, and so therefore it has to be replaced faster. Then there's the neutral cells, which mean really nothing, and especially when you consider the fact that they are not part of your germline cell or reproductive cells, so they're not going to be passed on to your children. They're mutations that are in some cells. In fact, there's lots of mutations in our body, but every cell is different. One cell has one mutation, another cell has another mutation. It's not like we've accumulated a lot of the same mutation. Okay, but so and these neutral ones, they become pretty much irrelevant, though they accidentally can cause evolutionary changes, especially if the mutations are in our reproductive cells. Okay, then there's the ones that are beneficial to our cells. Okay, and the only one that we really need to worry about is the ones that cause cancer. Okay, now cancer is obviously not beneficial to the human, but it sure is beneficial to that cell, because that cell now can grow happy and do everything it wants and kill you. Okay, but it doesn't really know it's killing you, but it's a very, cancer cells are pretty much a lot of times, sometimes they're very unhealthy and they're hard to grow and they die at a fast rate, but they still keep growing. But so the cancer cells are the one concern, but it turns out that your ability to get cancer, not just because of an accumulation of damage to the cells, your ability to get cancer increases when you get longer lived. And I'm going to try to avoid using the word old, because I don't like the word old. But the longer lived, and the immune system is also like an organ or a tissue. Okay, it has its frontline cells, and therefore, if your immune system is very effective at fighting cancers, and that's why cancer incidences are very rare when you're young, but then they get very common when you're older. And a major reason for that is that your immune system is failing. Your immune system is failing just like the other organ.
Yeah, that's such a key point, because I don't think a lot of people understand that actually cancer, if your immune system's operating as it should do, and it's firing on all cylinders, so to speak, you're much more unlikely to get cancer, and therefore supporting your immune system in whatever way you can is super crucial. Like your basics, like vitamin D and zinc and vitamin C and all these sort of things that are just basic things that are going to support your immune system, plus all the other more fancy things. But it's key.
But the bottom line where I'm going is that damage causes cells to be lost or killed, and other cells can divide to replace them. So why aren't we immortal like a bacteria culture is? Okay, so the big breakthrough came in 1961 when Leonard Hayflick showed that human cells have a limited number of times that they can divide. Okay, people thought he was an idiot at the time. They didn't believe it, but it's been reproduced 1,000 times, and now he's super famous. Should be getting a Nobel Prize for this discovery, and hopefully he will. But it's human cells can only divide a certain number of times, and therefore eventually you can't replace those damaged cells anymore. Okay, so what I want to say is that you have your frontline cells that are on the surface of the organ, let's say, but inside the organ you have your reserve cells. So I'm using like a military, like in a battle, you have your front line, and then when the frontline people start being eliminated, you bring in the reserves to fill in the spots. Okay, well, the same thing's happening in all of our tissues. Our tissues are at war constantly. Okay, so the reserve cells are our stem cells and our progenitor cells that really just have no trouble at all, just dividing and replacing by dividing and differentiating into our frontline cells. But as I said, that can only happen a certain number of times. And so let me take a typical, so the cells eventually, after they divide a certain number of times, they go into a phase called senescence.
Yeah.
And they can no longer divide, and they're still alive and they can function. They actually cause other damages to neighboring cells too. SASP is the abbreviation for which I'm going
associated secretory phenotype.
Yes.
Yeah. Yep.
And so the question really becomes, well, why do we have a limited number of cell divisions? And let me give you one example. Okay, so drinking alcohol kills liver cells.
Mhm.
Okay. So people that drink a lot, their frontline cells in their liver don't last a year.
Wow.
They're a shorter time. And so as a result, other cells have to replace those frontline cells more often.
And that's
and
aging because
yeah,
you're
well,
getting to the end of that Hayflick limit quicker.
yeah, you're getting to the Hayflick limit quicker. I didn't mention Hayflick limit, but that's the name of this thing that we call it now because of Leonard Hayflick. The cells eventually lose the ability to replace the damaged liver cells from the alcohol, and you get liver cirrhosis. Okay. And if you could keep those cells from reaching their Hayflick limit, you could drink all the alcohol you wanted and never get liver cirrhosis. But that's probably my favorite example.
Yeah,
because,
that's really good. And
you know,
Dr. Bill, so when the stem cells come out of the bone marrow and they start to differentiate, they're like splitting in two, and the stem cell goes out in circulation and then gets attracted to the different tissues, and which is complicated, but and then becomes the tissue of that cell, that organ that's needed. So a liver cell, a neuron, or whatever the case is. The cells that are in the bone marrow, I've interviewed Dr. Christian Drapeau, who's a stem cell researcher, and he has a product on the market that helps produce more stem cells, right, into circulation, helps release them out of the bone marrow into circulation. My question is, like, if I'm releasing more out of my bone marrow, am I then going through my stem cells quicker, or is the population just splitting and dividing, but not, you know where I'm heading with this?
oh
So
yeah, no. Okay, so mostly the stem cells in the bone marrow is mostly the hematopoietic stem cells.
yeah,
Okay, so you have other stem cells even within tissue, within organs. And it starts to beg the question, what is the definition of a stem cell?
yeah,
And I always say a stem cell is anything that can divide to produce another cell. So every cell has a stem cell, but the most of the stem cells in the bone marrow are the hematopoietic, so the blood stem cells. But we do have them lots of other places. But yeah, and when they divide to bring more cells, their telomeres get shorter. It's a common misconception that stem cells don't age, but they do age. Okay, they
right.
have the same age, just like, and they have a limited number of cell division, just like any other cell does. The only cell that's an exception to that is called human embryonic stem cells, or if you're a mouse, it'd be mouse embryonic stem cells. And those do have a unlimited number of cell divisions. And it was through that knowledge that we discovered what I'll be talking about next time, is the how not to age. Okay, so these progenitor cells and stem cells are dividing, they reach senescence and stuff like that. And we know that, like, when you're single cell embryo, that single cell can divide 100 times. That's it. And people think that can't be right. It's got to be able to divide more than that. But okay, I've got a doorbell ringing. Hold on. So a cell of a newborn embryo, let's say a single cell embryo, that can divide 100 times. And people often say, how could it only divide 100 times?
Yeah.
That's not enough.
No.
But when you do the math, you figure out the size of a cell, and you do the math, a single human cell dividing 100 times will make a mass larger than the planet Jupiter.
Okay? Oh, wow. So
and people don't actually realize it. Yeah, because 2, 4, 8, 16, this turns into a tremendous mass after 100 cell divisions. So 100 is plenty to allow a person to survive for a long time. In fact, the math puts it at, when you consider that frontline cells can only last about 1 year, the number of divisions, and you take into account that a single cell can divide 100 times only when it's a single cell embryo, that puts us at a theoretical maximum lifespan of 125 years.
Yeah.
Okay. So if human cells could divide 101 times, then we would live 1 year longer, that kind of thing. Okay, so they can only go that long. But from being a single cell embryo to go through all the cell divisions to become a newborn baby, you've already lost half of those. So
Yeah.
a newborn baby the cells in a newborn baby can only divide 50 times. And then when you still have a lot of cell division because you're growing, you're healing wounds, you're fighting infections, there's a lot of different things going on. And so eventually your cells get down to where you only have less than 10 cell divisions left. You're pretty much 90 plus years old at the time, and you have a theoretical maximum of 125. Okay, and nobody's ever lived that long. There's the most common documented case of somebody living that long turned out to be a case of a daughter pretending to be the mother. Okay, that's Jean Comment. Jean Comment.
Yeah.
Now who knows? There's another case of somebody living to be longer than 120. That might end up being something similar. But nobody's ever lived to be 125 in recorded history. The question becomes, why is there a limit on the number of cells, the time cells can divide? And this used to be something that we used to discuss when I was starting anti-aging clubs in high school and college. And we started thinking, how could a cell have a mechanism inside of it that tell it how many times it had divided and how many more times it can divide? You know, it's like, it doesn't have a calculator, it doesn't have a brain, things like that. And the analogy that I came up with, that I thought it was the best explanation, is that there has to be something like ride tickets at an amusement park.
Yeah.
Okay. Yeah. And every time a cell divides, it loses a ticket.
Yeah.
And I mean, what the hell? At least you could imagine a biological way that could happen, whereas other things just were too impossible to imagine. So I spent years after that wondering, what the hell are these ride tickets? Where are they? How do they work? And then in 1992, 1993, I was attending a conference and I heard all about the fact that telomeres, the very tips of our chromosomes, shorten every time a cell divides. They're not degraded. They're not unraveled. They're not all the different words that everybody uses. They're not damaged. And when a cell divides, so you have a parent cell and it makes two daughter cells, everything inside that parent cell needs to be duplicated so that when the daughter cells are produced, each daughter cell contains the equivalent of what the parent cell had. And that includes the DNA of the chromosomes, where all of our genes are. That has to be duplicated. But it turns out that our cells, when they duplicate DNA, they don't have the ability to duplicate all the way to the very end of the DNA. It's like the analogy I use is a bricklayer making a new row of bricks on a brick wall, and he's standing on the wall, walking backward, placing a brick. But when he gets to the end of the wall, he or she falls off, and the new row of bricks is shorter than the previous row of bricks.
That's a really good analogy. Yeah.
That's exactly what's happening in our cells. So our telomeres get shorter, not because of wear and tear. That's why I said the telomere shortening is the only hallmark of aging. This mechanism of action is not wear and tear. It's actually the lack of the ability of the cell to reproduce the DNA all the way to the end. So
how can we then slow down having to replicate those cells? Is that an option? You know, like if I live a lifestyle and I don't drink alcohol and I don't, you know, am I going to not have to divide as many cells? So when I'm speeding, or don't get any infections, because infections speed up the shortening because you're having to divide and create new cells.
Yeah.
So all of these
Well,
things are going to speed up. So that's still the wear and tear side of the telomere story, correct?
so when we get to the next webinar, when I talk about how not to age, I will talk about there's two things we can do. One is decrease the rate of cell division, and the other is decrease the rate of telomere short. Okay, so but yeah, there's a lot of things we can do to decrease the rate of cell division, but mostly only the things that that reverse the effects caused by poor lifestyle choices and poor things like because we like out drinking alcohol, we can decrease the rate of the cell division to replace the cells by quit drinking alcohol.
Yeah.
Same thing for smoking, same things for a lot of different things. But there is this basal level, okay? So good example is just blood pumping through our blood vessels, okay? Well, the blood vessels are lined with endothelial cells.
Yeah.
Well, these endothelial cells get stripped off just from the current of the blood running through the blood.
Sheer
And
force of the
we can't reduce that, okay? And so that's happening. So there's a turnover of endothelial cells, and it turns out from studies that we actually did 40 years ago when I was still at Geron Corporation, where we showed that the areas where there's a lot of plaque built up actually have already gone more cell divisions because of turbulence than because of turbulence damaging the endothelial cells and having to be replaced, than other places on the blood vessels where there's less turbulence.
Wow.
The study was done on the bifurcation. So just around your stomach area. So there's a major arteries and vessels going up and down your inside
aorta, yeah.
your body. And there's a bifurcation that essentially takes on one leg and the other leg. Well, at that bifurcation, there's a lot of turbulence. Okay.
Yeah.
And so we were able to study and find out that the loss of endothelial cells, the rate of loss of endothelial cells is much higher at that bifurcation than other
That's
places.
why people like my father died from an aortic aneurysm. Well,
Yeah.
he died of sepsis and the following on from the aortic aneurysm. But that aortic aneurysm would have been because he had damage in that bifurcation area that would have caused a blowout and an aneurysm in that point.
Well, he probably also had high blood pressure too, and other things that
he did, but he smoked. Dad smoked.
Smoking is going to increase aneurysms and things.
Yeah.
Like this poor lifestyle choices, because those all cause high blood pressure. They all cause conditions in your blood that increase the wear and tear of those cells at the high turbulence areas.
Yeah. And there's a genetic factor too, like we all have in our family a genetic, the 9p21 gene that makes it weak. So we've got to take extra special care of our endothelial cells, if you like. Otherwise, that's our weak point.
I keep scratching my neck because I was at my cabin yesterday and went out for a run and I got bit by 50 mosquitoes.
Well,
my neck and my legs are just itching.
You're causing inflammation and the speeding up of telomere shortening in the neck area right now.
Maybe. But so the telomeres, every time a cell divides, the telomeres get a little shorter.
Yeah.
And we know that from in vitro work, from growing human cells in a petri dish, that as soon as the telomeres, so telomeres you're conceived at 15,000 bases. When you're single cell embryo, your telomeres are 15,000 bases. Bases are units of DNA, and you can count them to measure the length of the DNA. Okay, so you got 15,000 bases of telomere sequence when you're first conceived. When you're finally born, you only have 10,000 bases.
Yes, you've lost a third already.
Yes, you've lost a third. But actually, you've lost half because you die of old age when your telomeres get 5,000
bases.
And they'll go into senescence when that telomeres get down to 5,000 senescence. So the first 5,000 bases at the inside the chromosome are actually, I don't know why they're there. They're just pointless because because you have to have a minimum length of at least 5,000 bases to keep the cell functioning normal.
Yeah.
Otherwise it goes into senescence. So you've lost half your cells by the time you're born and the other half for the rest of your life. And it turns out that when you do the math, it turns out that the maximum number of years that you can live is 125, just like from previous studies before we'd learned about telomere shorting. And there's something else I wanted to say was, yeah, well, it's just that this has been verified by every lab in the world that works with human cells in petri dishes.
And so this is the crux of aging then. Like this is we can do all the other hallmarks of aging, improve the immune system and reading of the chromosomes and the protein folding and all of that and have that optimized, but we're still going to die before 125 if we don't solve this problem.
I always say, no matter what else we do to solve the aging process, nothing is ever going to allow us to live longer and healthy than for longer than 125 years if we don't also solve the telomere shorting problem. So that's why I say that telomere shorting problem is the #1 problem we have to solve. And in the next webinar, I'll spend a lot of time talking about everything we're doing to solve that problem.
Okay.
And I'll also talk about the fact that there are things that you can do to increase or to decrease accelerated cell death. Okay, and that's like antioxidants, anti-inflammatories, meditation, yoga, quit smoking, quit being obese. One of the peculiar ones, which it's a really hard one to explain, but there's 2 studies supporting it, and that's pessimism. Pessimism has been shown to accelerate cell division and therefore accelerate telomere shorting. And so if you don't think you're going to live to be 100, you won't.
Yep.
And if you do think you'll live to be 100, you're more likely to.
Yeah.
But there's a few other things you can do, and this will breach on a little bit about my next webinar, but you can take antioxidants, you can take anti-inflammatories, you can find out what foods and things, lifestyle choices cause inflammation. Exercise is one of the things that I think is a good way to decrease inflammation, but only if you do it right, okay? Because inflammation, no exercise is going to increase inflammation. Too much tough exercise is going to increase inflammation. You and I, as ultramarathon runners, we should be therefore having tremendous aging, accelerated aging. But it turns out that when you are consistent in exercise, especially endurance exercise, when you're consistent, your body never recognizes the pain or joint stuff going on with your joints as injuries. Okay. No. And so it doesn't do anything about it. But if you're an occasional exerciser, you're the type of person that runs once every 2 weeks, then you go run a marathon, your body is going to have a tremendous inflammatory response.
You haven't built it, and you're going to be in pain and you're going to be suffering,
and doing damage. Take weeks to recover, and that's acceleration. But I'm sure you, from running all your races, and same with me, we've noticed that sometimes we can go out and run a 100-mile race, the next day run a 10K, okay, without any trouble. Well, maybe a little trouble. It's a lot easier than most people who are bedridden for weeks sometimes. But that's because our joints didn't get swollen, because we didn't get inflammation. And swelling is usually a result of inflammatory cells migrating to the injuries and stuff like that and causing the swelling.
And I think this is a really important point, like you've got to build up. So for those, like you have to, I'm really against people going and doing an ultra marathon when they haven't done the hard yards to build up to it, for example, because then they are going to cause themselves damage and do their body a real disservice. When you've built yourself up over a long period of time, then you're more likely to be able to cope with that stressor and you won't have that inflammatory over response. and like doing the extreme stuff that you and I did, maybe you less, but I certainly did have inflammation after running in the Himalayas or whatever, and it did do harm in the fact that I wasn't trained to that degree properly, perhaps, but I pushed through on the day, and that's pushing through is probably not the best way to do it. You should probably back off just before there. I mean, this is apart from the whole psychological benefits that you have from it, but just from a physical perspective, you really do have to prepare for those places.
I regret to say that you and I both accelerated our aging
Yes.
by demanding that ourselves finish that race in the Himalayas.
Yeah, that one really sped up the aging process.
and I'll tell you, the worst that happened to me was the intense blisters on my bottom of my feet, and it took weeks for those to heal. But okay, I always say, you mentioned the word cope with it, with things, and the way to cope is to keep it fun. Okay, and it's like, as long as you keep exercise and endurance exercise fun, and quit when it quits being fun, then you're okay. It's just that, and therefore, when you do that, you end up you can go longer and longer distances of keeping it fun. And that's why you and I can do these races. But still, when you enter a race like that, you still push yourself because you don't want to be a do not finish.
Yeah, you go beyond the fun part of those races, to be fair.
You gotta finish. You can't go home saying you dropped out of the race.
Well, you try not to. You give it everything that you don't. Yeah, for sure.
That probably wasn't the best thing to do, but I will never regret having done that race.
No, because you've got to live too, don't you, Dr. Bell? Like, at the end of the day, if we got to the end of life and we've lived it perfectly and we haven't done anything that was going to cause any harm and then we're still going to die, we haven't had the experiences that we've had, then that would be a shame too, right? So we've got to do this trade-off between what we actually want to achieve, and sometimes that's pushing beyond what would be healthy, so to speak.
I always say, what's the point of living a long time if you're not living? We can't be so bored with life that we live to be 125. We got to have
some things that shorten it. I agree. And so coming full circle, as we round out this section on how we age, is there any other things that from the other hallmarks of aging that you would say, okay, besides the telomere limit that we've established as our major issue in the whole aging game, and how we can't get at the moment beyond that 125, which is what you're working on and what you'll talk about next week, what lengthens telomeres and all of that. From the other hallmarks of aging, is there anything that you find really valuable that would help us understand how we age, from all the other 12 things that they've got, or 11 things besides the telomeres?
Well, I think they're all important. I mean, there's not a single hallmark of aging that I don't not believe in.
Right.
Okay.
They're correct in their theories, and
and but I am hoping that when we figure out a way to prevent telomere shortening, they become less relevant. But until then, the best thing you can be doing is to prevent the damage that is caused by all the hallmarks of aging. I don't have the list of the hallmarks of aging in front of me, but if you wanted to list a particular few, I can tell you.
Yeah, like protein misfolding, like what's going on in that hallmark of aging? This one that I've struggled a little bit to understand. So we produce proteins in our what do you call it, endoplasmic reticulum. We're making proteins, and these are sometimes getting misfolded. So these are 3D structures, basically, that the body is putting together. And what happens there?
But they're just clogging up the system. Okay, it's like accumulation of junk. That would fall under the accumulation of junk. Not everybody has it as bad as anybody else. The proper misfolding is sometimes a genetic result, is sometimes a lifestyle choice that's making certain proteins not work correctly, or not, like proteins that are involved in folding other proteins, let's say, are not correct, or proteins that are responsible for eliminating or removing improperly folded proteins aren't working enough, aren't working correctly. Those things, the net result is that it causes damage to the cell, and it causes the cell to die sooner than it would have if there wasn't this accumulation of improperly folded proteins that are junking up the system.
Mm-hmm. Yeah. So this is one, and if we look at some of the other things, like our immune system is another sort of area that I've been focusing on. How do we support our immune system from, like we've got, and I suppose this is an example of telomere shortening. Our thymus gland calcifies or becomes like a fatty sort of thing by the time we're 60, and it's not functioning anymore. And so we're reliant on how our immune system has learnt to recognize what a pathogen is, and which is a bacteria, and which is a something that's bad for us. And then that function starts to decline as we get older. Is that telomere shortening again at play?
Yeah, it is. But in the case of the thymus, I believe that the frontline cells in the thymus are so overworked that even under normal conditions, they do not survive a year. Okay, and so the thymus is, by the time you're 60 or something like that. Other people like probably the best person I know on the thymus is Greg Fay. Who, if you're not interviewing him, you should interview him. But he's studying, trying to figure out how to get the thymus to survive longer. And one of the things he's looking at is ways of keeping the telomeres longer. But it's still the same thing. It's like even under normal conditions, it's not going to last as long as the other organs, but you can accelerate its decline by poor lifestyle choices and diet, things like that but do whatever you can to decrease the chance that the immune system has to be fighting things all the time. Okay, so just don't get infected with the flu all the time. It's things like that. And stay away from COVID. COVID has shown a tremendous amount of accelerated aging. There's numerous publications now on it, and lengthening telomeres would allow people that had suffered from COVID and had accelerated aging to make that accelerated aging irrelevant. They could live normal lives, but yeah. So we are looking, and there's a lot of people looking at the idea of lengthening telomeres as a way to solve the long COVID problems.
Yeah, that would make sense. And then we've got like things like epigenetic alterations and mitochondrial dysfunction. And so mitochondrial dysfunction is another major player, isn't it? Like when your mitochondria, which are the little, energy factories in your cells that make the energy for that cell to function, and they're actually a bacteria from a not human origin. Originally way back in the day, and Dr. Bill, you know better how this works, but these are the little factories that are making energy, and they seem to be one of the major hallmarks of aging as we start to, or a cause of a lot of disease is when the mitochondria start malfunctioning or dysfunctional. What's your take on that? And
mitochondrial dysfunction is a major cause of aging.
Yeah.
What a lot of people don't understand is that most of the proteins that make up a mitochondria are actually encoded by the chromosome itself, the human chromosome. So there's a few proteins in the mitochondria DNA that play a role. But so keeping your chromosomes healthy by keeping telomeres long is also a way of keeping your mitochondria.
Wow, I didn't know that.
And mitochondria, they produce a lot of free radicals. And they damage DNA, but they also damage their own DNA, and they damage their own tissues, and or membranes.
They're easier to damage, isn't it? Their DNA, the mitochondrial DNA, is actually easier to damage than our DNA. It's got less.
It's probably harder to repair the damage, but I would say the damage is probably not more, but I'm not an expert on that. I would have to say that DNA damage is going to happen no matter what the where the DNA is.
Yeah.
But we do have repair mechanisms that are really good at repairing. And so that if there's a higher increase of mutation rates in mitochondria, it's going to be probably due to the fact that the repair mechanisms are actually incorrectly repairing the DNA.
Yeah.
Not the actual mutations occurring to begin with. Yeah, so yeah, there's so the mitochondria, yes, so damage. So one of the things that you can do is decrease your glucose intake,
Yeah, massively.
because
Yeah.
glucose goes through the what is it?
Electron transport chain and the
But before then, it's the what do you call it? The first steps from converting into lactate that goes into the
in
Krebs
the
cycle.
pyruvate and lactate.
Yeah, before pyruvate, what's that part called? I can't believe it.
So you got
Glycolysis.
glycolysis.
Glycolysis, yes.
Yeah.
So glycolysis, Krebs cycle, oxidative
Oxidative
phosphorylation.
phosphorylation. Yeah.
Those are the major three steps of glucose metabolism. And the result is that a lot of free radicals get produced from that.
Yeah.
And so a healthy diet, again, can play a role. But yeah, it's very important that we fix the mitochondria. But I do believe that lengthening telomeres is going to be a major factor in doing that.
As well. So it seems like it touches so many of the things. If you think about stem cell exhaustion, that's telomeres, really, isn't it? At its core is telomere shortening as well. You got the stem, and genomic instability is also part of the telomere story.
When telomeres get really short, mutation rates and chromosome rearrangements skyrocket.
Skyrocket because of telomere shortening. Once those base pairs get below that 5,000, that's when you really start to see things like cellular senescence is also related to telomere shortening.
Yes, we were the ones that first showed that. Okay, because before we discovered a way of lengthening telomeres, which is the enzyme telomerase, I discussed last time. Nobody knew exactly what caused senescence. Right? There was theories on what caused senescence, but everybody said senescence was irreversible. Once you went into senescence, you cannot come out of senescence, and you can't prevent senescence. But when we discovered the enzyme telomerase that lengthens telomeres, we were able to show in I think it was 1998 paper, maybe it was a 2000 paper. The first author is Bodnar, B-O-D-N-A-R. We were able to show in that paper that we actually abolished senescence. Okay, and it's the first time ever. And so now nobody says you can't reverse it and you can't prevent it, because we now know that in humans it's totally caused by let's say senescence is totally caused by telomere shortening, but quiescence, which is a very similar thing to senescence, is caused by other things, and quiescence is reversible.
Wow. So once it's at that early stage in its thing, it can be reversed, but once it gets to the full senescence stage, it can't be.
With lengthening telomeres, yes.
Yeah.
You can take cells that you can put the telomerase gene into cells, and you can have an on-off switch where you can turn it on or off, and you can let the cells get into senescence, turn the telomerase gene on to lengthen the telomeres, and that'll bring the cells out of senescence.
Wow.
That was discovered by the experiment that was done, that I just mentioned, was done by Jerry Shea and Woody Wright at University of Texas Southwestern.
And if you've got drugs and things that are and supplements that are on the market now, like Fisetin and rapamycin being a drug that gets rid of senescent cells, or starts to get rid of some of the senescent cells. As you rightly pointed out, if you got rid of too many senescent cells in the elderly population, they're disintegrated to dust because there's nothing left. Sort of like, there's a lot of senescent cells to.
I'm worried. I'm worried about let's say 110-year-old person using a and what do you call it? And a drug that,
Rapamycin. Yeah. Or
senolytic, senolytic
Yeah.
drug, a senolytic drug that actually kills senescent cells, because let's say the majority of the cells in the skin might be senescent, and if you kill them all, that will kill the
You've got
person.
nothing. You're in the yeah.
We don't know. Nobody's ever done that,
We
so I
don't
don't know.
know. No.
But I'm worried about it. But I think that combining senolytics with telomere lengthening would be the solution.
Yeah. Now you're
The
talking.
other thing, when you kill senescent cells with a senolytic, still another cell has to divide to replace that cell, which is actually now going to cause accelerated telomere shortening.
Yeah.
So it's I mean, senolytics is, I think, a short-term solution to the problem, but it's going to cause some major problems in the future. All the more reason why I
That's
want
your job to fix the telomere stuff, so that we can use our senolytics and use all these things that actually, like even like, skin resurfacing and lasering, all of that, microdermabrasion, all of that actually speeds up you get younger looking skin, and it is younger for a while, but you've actually created new cells, which has caused more cell division, which has caused more problems. So there's a lot of things that fall into that category, right? That are actually beneficial, but causing shortening of telomeres. So if Dr. Bill can fix the telomere problem, then we can go and use our microdermabrasion and our exercise to extremes, and do all of these things that could cause shortening of the telomeres, and then you can fix the telomeres for us. That would be great.
Anything you do that increases the rate of cell division is going to accelerate aging. So microdermabrasion, like you just mentioned, but also immune boosters, those are going to cause accelerated aging in the immune system, and even something like human growth hormone, which a lot of people are taking to build up muscle, that is causing cell division, which is going to accelerate telomere shortening.
And this is not to say, like, because this is a balance, right? Like, if you don't have any human growth hormone, you're going to have a lot of other problems, and you're going to die of other problems. So it's always this balancing act of how do you have enough IGF-1 and enough human growth hormone and enough testosterone and enough, human optimization, so that you live a functional, vital life. But on the other hand, you're speeding up the aging process, like it's this just terrible, damned if you do, damned if you don't scenario, calorie restriction.
A lot of my talks, I show a scale.
Yeah.
And I show how much it can go up and down on either way. And you're right. It's also another analogy I use is a tug of war. It's always a tug of war, back and forth between different things going on. Life is a tug of war. Everything about it, tug of war.
So it's not that microdermabrasion is bad and you should never do it, but understand what's happening, and then you better balance out the other side, and picking and choosing, IGF-1's one of those really difficult ones, like has so many benefits. Like if I'm trying to increase mum's IGF-1 levels at the moment for her brain cognition, for her bone density and all of that sort of stuff. But am I speeding up the telomere shortening process in the meantime? But is it too low that she won't survive if I don't do that? Like you're sort of in this damned if you do, damned if you don't scenario. And so this is why I think that the next webinar is just going to be absolutely fascinating, because there's this whole telomere story of how, and we've shown today how many of the hallmarks of aging it actually influences, and as a part of those story of all those other, it's sort of the linchpin. So we can then be able to have this vital, strong life, have our optimized testosterone and human growth hormone and IGF-1 and, all of those mTOR sort of pathways going, build muscle, be better, but not shorten our lifespan with it, from the telomere.
As I always say in my talks, microdermabrasion, human growth hormone, things like that are good, okay? Because what's the point of living a long time if you're not living? Okay.
If you're not living, you feel like you're half dead because you've got no energy and you've got no muscles and you've got no functionality.
You don't want to miss out on you don't want to miss out on all the great things about life, because living is the greatest thing that ever happened to us. You don't want to miss out on all that just to be able to live as long as possible. I mean,
just to have the long telomeres.
Do it. I will fix the problem. I will fix the problem before most people have to worry about it.
And on that point, I think we wrap it up for today, Dr. Bill. I think that was actually a really good jumping off point for our very important webinar, which is the next one on how not to age and what Dr. Bill is doing and working on. And so make sure you stay tuned for that one. And now you've got the history, the background, the why, the how, the what, and now it's how not to, which is the key point of this. So thanks, Dr. Bill, for sharing your insights today, and really appreciate you.
All right. Thank you.
Thanks so much for watching, and we hope you enjoyed this video. Please like, comment, hit the notification bell and subscribe. And of course, share it with just one person who you think could really benefit from this content. Click here to watch last week's episode, and click here for my website, and click here to watch a video you may not have seen yet.